Good evening. This is the session 6 for polymer reaction engineering, where we'll be having a live session and discuss the sample problems so that you can solve your assignments for this week. My name is Rohan Jadhav and I'm the TA concerned for this section. So starting from the first question, uh, in this section we'll be discussing more about radical chain polymerization and ionic chain polymerization processes. So the first question we have is the termination in ionic chain polymerization uh, can proceed through recombination of counter ions, forming a sterically hindered ion having very broad charge distribution, forming a sterically hindered ion having very narrow charge distribution. So let's take a look at all these options. First, we have recombination of counter ions. Recombination of counter ions is like it requires an external agent for uh, in ionic chain polymerization. The termination step requires an external agent for the reaction to terminate. So because since like charges repel each other and hence they cannot form a new bond to terminate the reaction, external agent is required. So forming a sterically hindered ion having very broad charge distribution, uh, since just as I described right now, that like charges repel each other. Uh, so they don't, the termination of the reaction has to be proceeded by addition of some external agent and ionic polymerization. So formation of a sterically hindered ion having very broad charge distribution can act can act as a promoter to uh, promoter for the like charges to react with each other and terminate the reaction. So, forming a sterically hindered ion having very broad charge distribution uh, is the possible choice for termination of ionic chain polymerization. Moving on to the next question. In radical chain polymerization, the term dead polymer signifies what? So, a dead polymer, in its general basic definition, is a polymer which is incapable of growth. So, if we take a polymer chain like this, uh, it cannot grow by itself any further. Like no more monomers can be added to it, and even if extra monomers are added, they won't react to increase the length of the polymer chain because there are no active centers left for polymerization reaction. So in radical chain polymerization, from the basic definition, we know that the stopping of the growth of the propagating radical, which attaches itself to the monomer chains and extends the polymerization process to form the long chain polymers. When the propagating radical's growth stops, the radical chain polymerization will come to a halt and terminate. So it won't come to a halt, it will give rise to a dead polymer. So in that case, the propagating radicals cessation growth will give you a dead polymer. Which among the following options will show the highest positive resonance effect? So uh, in the plus R effect, that is the resonance effect, the electron transfers from functional group to the system. The donation of electrons from the functional group to the system is what determines the resonance effect, high positive resonance effect. So in all the species which are shown here, fluorine, chlorine, OH minus, NO2, and Cl minus, we can see that if you have come across uh, the hierarchy of positive resonance ion functional groups, you see that OH minus has the highest resonance effect. And among these halogens, on the other hand, they are highly electronegative and they cannot, they produce the inducive effect or I effect. So they are on the last section of the hierarchy showing the positive resonance effect. So all these options will cancel out, and OH minus group is the one which produces the highest positive resonance effect by donation of electrons to the system. It has the highest lung mass, so that's why it is able to donate the electrons. Going on to the next question. We have which of the following are not the characteristics of the chain growth polymers? So in chain growth polymerization, you know that a small amount of monomers reacting itself will create uh, large molecular weight polymers. So a high molecular weight polymer formation using unsaturated monomers. Yes, this is actually a characteristic of the chain group polymers. Moving on. Bifunctional or multifunctional monomers form high molecular weight chain polymer. This is not the characteristic of a chain growth polymer. This is a characteristic of a step growth polymer, where bifunctional and multifunctional monomers are able to form high molecular weight polymer chain. Because chain growth polymers does not require bifunctional and multifunctional monomers, and a small amount of monomer reacting itself can give rise to high molecular weight chain polymers. Initiators are required to start the reaction. Yes, initiators are required to start the reaction. So this is also a characteristic of the chain growth polymer by basic definition. So since we are supposed to find the characteristics which are not defining the chain growth polymers, that would be first one would be this one, and next would be propagation occurs till the end of monomer without termination. This propagation will occur for the till the end of the monomers without the termination reaction, and that this is also not the characteristic of a chain growth polymer. So the correct answer would be the second one and the fourth. Moving on to the next question, we have moderate polarity solvents are preferable in ionic polymerization because we have to fill the blank. Then the preferable solvent as per the polarity can be another blank, and we have to choose the correct options. So in ionic polymerization process, the reactivity of the ion increases with increase in polarity of the solvent body. So if you have high like high polarity solvent would give you high rate of reaction and high molecular weight. But there is a catch that high polarity solvents can react very easily with initiators and completely stop the reaction. So that's why in that case we have to use moderate polarity solvents. Since high polarity solvents can easily make stable complexes or completely kill the initiator. So this is the first blank, as you can see. And then next we have the preferable solvent as per the polarity can be uh, since water has a very high polarity, water cannot be chosen for this moderate polarity solvent. And on the other hand, ethylene dichloride is a solvent with moderate polarity, so ethylene dichloride can be used as a moderate polarity solvent. So the answer for this is 1 and 4. Moving on to the next one. Nitriles are electron withdrawing functional groups and can decrease the electron density over the carbon-carbon double bond, resulting in the development of partial positive charge over the carbon atom, and hence such monomers are facilitated by which of the following processes. So you can see that since nitriles are electron withdrawing group and they are reducing the electron density over the carbon-carbon double bond, and a partial positive charge is getting developed. This points to the anionic chain growth polymerization process. Since the positive charge is being formed over the carbon atom because the function nitrile functional group is decreasing the electron density, an ionic chain growth process will be applied for the polymerization in this. So the correct answer will be anionic chain growth polymerization. Moving on to the next one. An engineer is wishing to develop a high molecular weight polymer with lesser reaction. Which of the following types of polymerization process should be used? So, uh, for a high molecule for formation of high molecular weight polymer, the one of the go-to processes is chain polymerization process. In chain polymerization process, even with a small amount of monomers, large molecular weight polymer chains can be formed easily. So that's why chain polymerization process uh, can be used to form a high molecular weight polymer. Next, But there is a second part of the question also, that lesser reaction time is required. So in case of forming, in case of having lesser reaction times, ionic polymerization also comes to mind, because ionic polymerization is actually very fast, and its reaction rates are uh, almost 3 to 4 times faster than a radical polymerization process, and even compared to step growth polymerization process. So ionic polymerization can form both high molecular weight polymers within a less reaction time, and chain growth polymerization process also can form very stable high molecular weight polymer chains. So uh, for for developing a process requiring high molecular weight polymer with lesser reaction time, the polymerization schemes to be used are chain polymerization and ionic polymerization process. So here we have isorigid polymers have unique head-tail placements, while air-rigid polymers compose of random head-tail and head-head placements. In statement 2, we have syndio-rigid polymers composed of alternating head-tail and head-head placement. So you can imagine isorigid, air-rigid, and syndio-rigid polymers with respect to their tacticity, how we define tacticity in the earlier classes. So in isorigid polymers, unique head-tail placement is observed. Like either they can be on a single side, or two can be on the two head-tail placements can be on a single side, on and the others on the other side. And whereas arygid polymers have irregular arrangement, and random head-tail and head-head placements are there. Whereas syndio-rigid polymers have alternating head-tail and head-head placements. So with that definition, statement one is true and statement two is also true. From the basic definition of isorigid, arygid and syndio-rigid polymer. So during the radical chain polymerization process, radical chain polymerization operating temperature possesses moderate but positive effect on increasing the degree of head-to-head placement of vinyl group. Formation of in polymerization process of polyvinyl acetate, the vinyl group's head-to-head placement is actually affected by the moderate by the operating temperature, but moderately, not that not a major factor, but it's a positive effect since the polymerization process, the degree of head-to-head placements of the vinyl groups is more ordered, and it is easily influenced by a slight increase in temperature. From around 40 to 100 degrees Celsius itself will give you a positive effect in the head-to-head placement of the vinyl groups. So yes, temperature does affect the radical chain polymerization uh, process moderately. Moving on, the electron blank functional groups like blank and increases the electron density over carbon-carbon double bond of the system. This leads to facilitate the cationic polymerization of the monomer. So, as we discussed in the previous question right here, that uh, we already know that nitriles are electron withdrawing functional groups. Electron withdrawing functional groups that decrease the electron density over carbon-carbon double bonds. Here, we need donating functional groups so that, as written here, increase the electron density over carbon-carbon double bond. Increase in the electron density of carbon-carbon double bond will only occur when electrons are transferred from the functional group to the system, to the carbon-carbon double bond system. So, since the nitriles are withdrawing groups, so these options these options would be incorrect. Now, since electron donating functional groups would be the correct answer in that case. And like alkoxy group. Alkoxy group is an electron donating functional group which increases the electron density over the carbon-carbon double bond of the system. This leads to facilitate the cationic polymerization of the monomer. Since the electrons are being donated to the carbon-carbon double bond system, the alkoxy group will facilitate the cationic polymerization of the monomer in this case. So this This session was mostly based on theory since you are learning about the ionic and radical polymerization processes. So this was just to give you a basic, these questions were just to give you a basic understanding of how the radical chain polymerization and ionic polymerization processes occur and what are the parameters affecting these processes.